Good morning everyone and welcome back. In the last class we have studied the molar quantities and we have seen that these intrinsic quantities do not depend on mass or the scale. So we can write them as, in case of enthalpy, delta small h, Gibbs free energy as delta small g, and then entropy as delta small s. Delta corresponds to change in the system when system undergoes from state 1 to 2. Whereas extrinsic quantities depend on mass or the scale of the system. So we can write this enthalpies, Gibbs free energy and entropies as delta capital H, delta capital G and delta capital S. So we have also seen that enthalpy of reaction is nothing but U plus PV, and we differentiated and we have shown that this enthalpy change is same as the heat transferred in a reversible process. So let us take these equations ahead. And we can say that for a constant pressure reaction, this enthalpy change basically expresses the amount of heat that could be evolved by the reaction. So this is for constant pressure process. So we can say that dH is equal to TdS. I am writing the equations again. TdS is equal to dQ. So let us take the conventional reaction that we have been using so far. So H2 plus O2. Let us understand what happens with this reaction. So this is an exothermic reaction. Let me write this up. This is an exothermic reaction. What does it mean? It means that this reaction, while it is undergoing, will also evolve heat. It will release the heat along with the other byproducts. So since this is an exothermic reaction, it will release the heat. So this we can write this dQ in this, for this type of reaction, is negative, right? So since dQ is negative, we can also write TdS is negative, and in other words your dH, that is change in the enthalpy, is also negative. What does it imply? It implies that this, I can write here, that in case of thermodynamics or in the thermodynamic world, we have this, when enthalpy is negative, it means it is an exothermic reaction, which is what is happening with our case. And if dQ is negative, what does it mean? I can write it here. So when dQ is negative, work is, sorry, I want to say dW. When dW is negative, work is done on the system, or this is negative. When it is positive, this work is done by the system. This is very important. So in our case, the dH is negative, means the heat is released by the system, and we can consider this enthalpy. It's very simple to understand, very easy to remember as well, because we can treat this enthalpy as a cash. Let's example, this can take this enthalpy as a cash. So when we give out the cash, we are basically losing our money. So in that case, it can be taken as negative, and when we receive money, like when we receive the energy in this thermodynamic world, it is taken as a positive term. So that's how we have got to know that enthalpy in our case is negative and it is an exothermic reaction. So we can go ahead and we can write dH is equal to TdS is equal to du plus dW. We can generalize this work. We exclusively do not say that this work is mechanical work or electrical work also. It is a general dW that we have written, and we can say that heat is evolved by the reaction due to changes in the internal energy of the system after accounting for any energy that goes the work. So basically the heat will be released by the reaction, any reaction, once the changes in the internal energy, or rather the heat is evolved by the any reaction. Once the work is done, the remaining amount is basically used for changing in the internal energy of the system. So this internal energy, if we try to understand internal energy, I can write as I E is mainly due to reconfiguration of the chemical bonds. Instead of bonds, let me write chemical bonds. So if I write H2 and O2, they have got higher internal energy, or I would say with respect to bond energy, their internal energy is more, and this H2O is got lower internal energy. Again I am writing with respect to bond energy. So this difference in bond energies of reactant, that is H2 and O2, and product H2O in case of fuel cells, is released as the energy or work, as work or energy, and rest is evolved as heat. And that is how this H2 and O2 giving H2O releases the heat, because not all the energy, the difference in this bond energy is converted into work. Some portion of that is converted into work, and the rest is evolved as an heat, or rather is given out as an heat. So I can write dH is equal to TdS is equal to du plus ddu. I am rewriting the expression. So this du is basically heat, as just mentioned in the last slide, and this work is basically some work. We don't know how much work that reaction will lead to. So this is what we are going to find out in this course, and this heat which is released as a changes in the internal energy. So this enthalpy change, this enthalpy change associated with the combustion or combustion reaction is called heat of reaction, or I would say heat of combustion. So if we have a combustion of H2 and O2, this is enthalpy will call as heat of reaction, otherwise it will just an enthalpy. So this dH is nothing but TdS, which is also equal to du, or this enthalpy is also called as enthalpy of the reaction. Let me abbreviate this as Rxn or delta This is extrinsic quantity, this is intrinsic quantity. So that is what leads to, if we electrochemically convert the reactant species, that H2 and O2 into water, some amount of enthalpy will be converted into work and the rest will be released as a heat. And if the same reaction is taken place in the combustion chamber, or if we, in other words, if we burn the reactant species, the enthalpy change is nothing but the heat of reaction, and that is what is mentioned here. Let us move on and we will try to understand the thermodynamic potentials, very important. Thermodynamic potentials. So, we have 4 thermodynamic potentials, U, F, and we have enthalpy and the Gibbs free energy. Let me put them in the box. So, this is minus Ts and this is minus Ts and this is plus PV. U is internal energy, F is Helmholtz potential, H is your enthalpy and G is your Gibbs free energy. Let me write this up. U is internal energy, F is Helmholtz free energy, which is nothing but U. So, if I want to go from U, which is equal to minus Ts, so U minus Ts is basically F. So, we have to subtract this, or rather add this minus Ts to U, so that we can reach the this term particularly, and then we also know H is enthalpy, which is equal to, if I want to go from U, it is U plus PV, right, and G is your Gibbs free energy, which is nothing but H minus Ts, and I can write H as right U plus PV, which is H, and this minus Ts will remain same here. So, this is your Gibbs free energy. So, what is Helmholtz free energy and what is Gibbs free energy? So, Gibbs free energy is nothing but energy associated with the closed system when pressure and temperature are constant. Okay, this is the constant. And what is Helmholtz free energy? Is the maximum useful work, that can be extracted from a closed system again, but here is a change. Here your volume and temperature are constant. So, that is the difference. So, when it comes to the fuel cells or electrolyzers, most of the cases we have pressure and temperature being constant. That is why we will be using Gibbs free energy instead of Helmholtz free energy. So, we have already seen this. Let us get these molar quantities one more time. Let us write them up one more time. So, capital G is basically Gibbs free energy. Let us specify them. So, for a system change, when the system undergoes from state 1 to state 2, so then that is where we observe the change. So, that delta G, when we write delta G, is the change in the Gibbs free energy when the system change from state 1 to state 2. This is the extrinsic quantity, we have seen this before. And how is your intrinsic? This is delta G. I can write G naught, delta G naught. So, when G naught, when we write G naught, it is at the STP, standard temperature and pressure conditions. So, we can also write entropy. So, this is delta S naught, this will be delta small s naught, and we can, and the units here probably will be in the kilojoules, since we are talking about the extrinsic quantities. When it comes to intrinsic quantities, this will be in kilojoules per mole. So, this becomes the molar quantity, and like I said, delta basically expresses the change during the reaction when it goes from state 1 to state 2, that is the delta. So, let us focus this on Gibbs free energy. So, when delta G, let us write delta G reaction is greater than 0, less than 0 or is equal to 0. When delta G reaction is greater than 0, it is positive term. It is basically, let me write, it is a positive term, which means the reaction is endothermic, meaning the reaction needs energy from its surrounding in order to go from state 1 to state 2. So, that is what endothermic reaction means. When the Gibbs free energy is less than 0, it is negative, it means it is exothermic reaction, and when it is 0, it is reversible, right. So, how do we find out this enthalpy of the reaction? How do we find out this Gibbs free reaction? Let us understand that. So, let us write to find out the reaction enthalpies. Right. So, let us first write delta H is basically, it is an output of, or rather output of difference in the bond energy. So, that is your enthalpy of the reaction, which we know. So, this bond energies, as we can see, this is slightly awkward term when it comes to calculations of the bond energies, calculation of the enthalpy. So, we have to convert these bond energies into some useful or measurable terms, and that is where we go to the delta or enthalpy of the formation. So, how do we write enthalpies of the formation? So, delta H of species I, and this is the cap. So, how do we read this? It is the basically how much enthalpy is required. You know, this term is important. How much enthalpy is required to form 1 mole of chemical species. The species is I here. This is your species I at standard temperature and pressure conditions from the reference species. So, this is what enthalpy of the formation. So, delta HF stands for enthalpy of the formation, 0 stands for it is at STP, and this cap signifies it is a vector quantity. So, this is what is easy to calculate. So, we will find out the enthalpy of formations of the different chemical species, and then for any given reaction we can subtract the product reactant species enthalpy of formation from the product from that of the product species, and then we can find out the enthalpy of that particular reaction. So, that is how we will proceed. And we can basically avoid these calculations of bond energies. So, if I generalize, let us say we have a reaction AA plus BB going to say capital M plus N capital N. So, there are reactant species A and B converted into M and N, that is product species. I can write enthalpy of this reaction as, like I said earlier, we have to subtract the reactant species and their formation enthalpies from the product and formation of enthalpies. So, we have to find out the enthalpy of formations, that is delta H naught, species is I, so here species is M, capital M, and it is as M moles, so we have to multiply M moles here, plus similarly we will go ahead with the enthalpy of formation of, forgot to write F here, F species N, and it is again has got N moles here, so I am multiplying N moles. So this is the enthalpy of formation of products, and now we need to subtract the enthalpy of the reactions of the respective reactant species. So let us move on, and we can write enthalpy of the formation of species A, this has got A moles, plus enthalpy of formation of B species, and it has got B moles. So these are the reference formation species. Since we are operating at STP or we are calculating at STP, we have to find out the enthalpy of the respective chemical species, that we will find out enthalpy of the reaction at STP. Okay. So since the formation enthalpy is at STP, we have to we will find out the enthalpy of reaction at STP. So if this the enthalpy of reaction is negative, which means it is an exothermic, we have seen this earlier, exothermic reaction, right, and if it is positive, this is an endothermic reaction. So here, which means the heat is released, let me write it in capital letters, and here heat is required, or rather it will be absorbed. Right. So this is the difference. If the enthalpy of reaction is negative, it will be straight away, it will do some work and also release the heat. So let us also understand on what factors this enthalpy of the reaction depends on. So let us first understand its dependence on the temperature. So dependence of enthalpy on temperature. Okay, let us first understand this. So basically, amount of heat, sorry, I forgot to mention it is a title, amount of heat energy that a substance can absorb, and this changes with the temperature. And this is what we are going to observe or rather record. So how does it depend? Now this is enthalpy of formation, but this is no more at STP because now we are deviating it from standard temperature and pressure conditions. So we cannot write 0 here. However, this enthalpy of formation at arbitrary temperature is equal to enthalpy of formation at STP plus, it depends on the heat capacities, which is function of temperature, and this goes from T naught to T. So T naught is your temperature at standard temperature pressure conditions, and T is your arbitrary temperature. So this is your heat capacity, right, when the pressure is constant, and this is your formation enthalpy at STP, and this is your formation enthalpy at temperature T, which is not equal to T naught. So this T is not equal to T naught. This can also be, I can write this the reference formation enthalpy. This is the relation with respect to the enthalpy of formation. When we want to find out the enthalpy of formation, we have to first get the reference enthalpy, reference formation enthalpy, and we also need to know the heat capacities and its dependence on the temperature. Once we get to know this, we can find out the enthalpy of the formation at any arbitrary temperature T. Same also goes with the entropy. So, we can write entropy is equal to reference entropy plus, this also depends on the heat capacities, which is function of temperature divided by T dt. So, we need to read this CPT with as a function of temperature, not the multiplication of Cp and T in both the formulae. So, once we know the reference enthalpy of formation, reference entropies, we can find out the arbitrary enthalpy of formation and arbitrary entropy, and then we can ultimately find out the enthalpy of the reaction and of course the Gibbs free energy. So, if we look at this formation and enthalpies and the entropies, we can see that they are dependent on the heat capacities. In case of solids and liquids, these heat capacities do not change much with the temperature. However, in case of gases, this heat capacities vary drastically as and when the temperature is changed, and that is one of the reasons why we have to take them into consideration. And this is why the enthalpy of formations as well as the entropies will also change drastically as and when the temperature is changed. So, with that we will stop here and we will take on with the next session in the upcoming classes. Thank you.